Welcome to this explainer. Okay, today we're looking at a breakthrough that's literally happening right now in labs all across the globe. We're standing right on the precipice of advanced quantum computing and next-generation nanoelectronics. But here's the catch. To actually unlock this new era, we have to build smaller, cleaner, and way more precisely than humanity ever has before. Okay, let's dive into this. If the potential of quantum computing is so absolutely enormous, why aren't we all carrying quantum smartphones in our pockets right now? Like, what microscopic roadblock is currently delaying our quantum future? Well, to figure out the problem, we really need to understand how these advanced electronic components are actually made. And honestly, more importantly, what happens when human clumsiness, on a literally unimaginably tiny scale, gets in the way of perfect physics.
Section 1. Building at the atomic level. Zooming in on ultra-thin materials.
Let's shift our perspective all the way down to the atomic level, right, where the actual building happens. You'll hear the term 2D heterostructures. Now, I know that sounds incredibly complex, but just think of it like playing with the world's absolutely tiniest, flattest Lego bricks. Scientists are taking ultra-thin materials that are literally just a few atoms thick, things like graphene, and stacking them up to build the circuitry for advanced electronic devices. We are essentially playing architect with the fundamental building blocks of the universe.
But we aren't just stacking them straight up and down. When scientists precisely stack these perfectly flat atomic layers, like graphene and another material called hexagonal boron nitride, and they meticulously control the specific angle between those layers, wow, something totally magical happens. The material just stops behaving normally. It unlocks entirely new realms of science. These carefully angled atomic stacks start exhibiting entirely new properties that simply don't exist in bulky, everyday materials. It's pushing the boundaries of what we even thought was possible in physics. Section 2. The contamination problem, when sticky tape ruins the nanoelectronics. So, as brilliant as this atomic stacking is in theory, the way we actually go about doing it right now has a massive, messy flaw. See, current manufacturing methods rely on these synthetic polymers that act a whole lot like sticky tape to assemble the layers. And just like cheap tape on a clean window, they leave behind this gummy, microscopic residue. Imagine trying to build a perfectly pristine Lego tower, but your hands are completely covered in sticky syrup. That leftover residue totally contaminates the tiny structures, and it completely disrupts the device's performance. They just don't function the way they're supposed to. And look, this isn't just some minor inconvenience. It's a monumental roadblock. As Professor Alexey Berdyugin from the National University of Singapore emphasizes, building atomic stacks without any contamination is a major challenge in nanotechnology. This almost invisible residue is a massive headache for researchers all over the world. When you're working at a scale where a single atom out of place actually matters, a smear of leftover synthetic polymer is basically an insurmountable mountain of trash. Section 3. The mica solution, a simple, natural mineral to the rescue. Well, a recent breakthrough published in Nature Communications by researchers at the University of Southampton and the National University of Singapore offers a solution that's honestly as elegant as it is surprising. Instead of inventing some hyper-complex synthetic chemical to solve this sticky polymer problem, they literally turned to nature. They just replaced the messy synthetic polymers with the natural mineral muscovite, which is commonly known as mica. Yep, mica, that everyday naturally occurring inorganic crystal you might have actually seen sparkling in rocks during a hike. That is now being used to expertly stock atomically thin materials. Crazy, right? And this brilliantly illustrates the real core of the breakthrough. Just look at the contrast here. With our old method, the synthetic polymers, they're soft, they're sticky, they leave all that microscopic residue, and they disrupt performance. But then look at inorganic mica. It naturally cleaves into layers that are atomically flat. It provides an ultra-clean surface, perfectly avoiding the contamination that ruins our precious quantum stacks. It's exactly like swapping out a sticky glue-covered glove for a pair of perfectly smooth, sterile titanium tweezers. Let's look really closely at Professor Berdyugin's exact explanation for why this works so flawlessly. He says, because mica is an inorganic crystal rather than a soft polymer, it avoids many of the contamination issues that plague conventional methods. It comes down to the physical nature of the material itself. It doesn't break down into gooey residue. It's a hard, stable crystal that allows these ultra-sensitive electronic components to finally function at their absolute full potential, totally free from the microscopic gunk that was holding them back. Section 4. Unlocking exotic new physics. Precision without the microscopic mess. So, we've solved the sticky tape problem. But why does this actually matter for the rest of us? Let's look at what this crystal clear precision allows us to achieve. The lead author, Dr. Makar Shishkins, points out that this new method is not just cleaner, but it's cheaper too. He notes that this level of precision is vital for quantum material research, where even a tiny amount of contamination can obscure the results. Think about it. Trying to observe these incredibly faint, fragile quantum states with polymer residue in the way is basically like trying to listen to a tiny whisper while standing right next to a jet engine. By giving scientists a pristine, flawless alignment method, we're suddenly opening a clear window into entirely new physics.
So, the crucial point is exactly what this flawless alignment unlocks. By mastering this ultra-clean assembly using mica, scientists can reliably create structures that exhibit exotic superconductivity. And that means electricity flowing with absolutely zero wasted energy. Zero. They can create tunable magnetism right at the atomic scale. And looking toward everyday consumer technology, this exact process is viewed as a critical step toward future nanoelectronics, eventually paving the way for microchips that are dramatically faster and way more reliable than anything we have today. We are finally unlocking the full, unadulterated power of 2D heterostructure electronics. Section 5. The Future of Nanoelectronics, Accelerating the Next Quantum Leap. It's just amazing how a single, seemingly minor laboratory adjustment can shift an entire field of science. For anyone following how technology advances, this right here is your core takeaway. An ultra-clean fabrication method isn't just some housekeeping update for laboratories. It is literally the critical runway for quantum technology. See, we already had the brilliant blueprints for these 2D electronic devices, but our tools were just too messy to actually build them properly. With mica, we finally cleaned up our act. The path is completely clear for the next generation of quantum devices. Which leaves us with a truly exciting prospect. We just solved one of the absolute biggest roadblocks in nanotechnology simply by looking closely at a common, sparkling rock found in nature. If replacing sticky synthetic polymers with a simple, natural mineral like mica can unlock the sheer power of the quantum era, you have to wonder, what other natural solutions are waiting just beneath our feet to help us build the future? Think about that as you consider where technology is headed next. Thank you so much for joining me for this explainer, and definitely keep your eyes open because that next quantum leap is closer than you think.